Today we're going to be answering some sample circuit problems. Let's begin. First problem. Use both resistance and source combinations as well as current division on the circuit to find the equivalent resistance, the total current, and the power absorbed by the 10 ohm and the 12 ohm resistor of the circuit shown. So this is our circuit, and you will notice here that this is a short circuit. It is a short circuit because it uh, it is directly connected to this node right here. What this tells us is that the current will just pass this circuit and it will not go through these resistors because well, this has less resistance, so the current will just pass right here, but we'll get into that later. So one strategy that you can use to answer these kinds of circuits is to redraw. So this is our circuit, and then we can redraw this to make it simpler. So this is the same circuit, and I will prove it to you. So it is the same circuit because these circuits are parallel with each other, same as these. So they are just representing the same branch. Same with these parallel. It's the same. And they are connected by this circuit, which is this one right here. And so now it is in a more familiar illustration. So another thing that we can do to simplify this is to combine these parallel circuits so that we can make them into series. So the solution to combining parallels are 1 over R, which is 10 ohms, 1 over 10, plus the resistor parallel to it, which is 40 ohms, 1 over 40 ohms. That is equivalent to 1 over 8, and we take the reciprocal of this, and that will be our resistance for these parallel circuits, 8 ohms. We will do the same procedure with the other parallel circuit. So 1 over 15 plus 1 over 60 is equal to 1 over 12. We take the reciprocal of this and we get 12 ohms. And so our circuit will now look like this. That is our 8 ohms and our 12 ohms resistor. Now we can further simplify this by adding all these circuits which are in, all these resistors which are in series with one another. So to add up resistors in series, simply add them. So 2 plus 8 plus 12 plus 3 plus 1 plus, now as what I've mentioned here, this is a short circuit, so our current will immediately pass through this branch here, and they will not go to these resistors right here because, well, zero resistance is better because the current is able to pass through here easier, so the current will most definitely be passing this, so it is plus 0 resistance plus 2 ohms. So now we have 28 ohms total resistance. So this is our circuit right now, and then to further simplify this, we can add our independent voltage sources. So we have two in this case. We have 150 volts and 30 volts, but as you can see, they have opposite polarities. So if we use Kirchhoff's voltage law here, we'll go on a clockwise direction and we will get the polarity which we get first. So in this case, we have positive 30 volts minus 150 volts. And so we get negative 120 volts, or simply 120 volts. So this is our circuit now. And so, now that we have our total voltage and our total resistance of this circuit, we can now solve for our total current. We can use Ohm's law, which is V is equals to IR, and then we can derive I is equals to VR, and we can use our variables here. So we have 120 volts over 28 ohms. That will give us 30 over 70, 30 over 7 amperes. Now, solving for the current at our 10 ohm resistor using current divider. As you remember, the principle is that if the circuit is in series, the current is the same. The current stays the same, and so in this path right here, our current is currently at 30 over 7 amperes. Right, so there's 30 over 7 amperes there. Now, when it arrives here, it becomes parallel, and so our current does not stay the same anymore. So our current changes, and so we use current divider to find the current which goes into our 10 ohms resistors. So the solution is take the opposite resistance and make it and use it as a numerator, 40 over 40, and add the resistor that is parallel to it. So 40 over 40 plus 10, and then you multiply it by the current that is going into your parallel circuit. So that is 30 over 7 amperes. So you will get 24 over 7 amperes. This is the current that is going to your 10 ohm resistor. So now that we have our current, we can now solve for our power. Solving for the power of our 10 ohm resistor is simply we use P is equals to IV, or we can derive P is equals to I squared over R. I squared times R, sorry. So we already got our I, which is 24 over 7 squared, times 10. 10 is our resistance, and so we get 117.55 watts of power. And well, the next question is, what is the current and the power drawn by our 12 ohm resistor? Well, as I have mentioned a while ago, this is a closed circuit. No current is going through our 12 ohm resistor, meaning no current means no power. So yeah, power is 0, as well as current for our 12 ohm resistor. So this is our entire solution sheet. Feel free to pause the video so that you can get a more clear look, and then we will head on to our next problem. Next, we are going to be solving this problem. Determine the power received by each of the resistors in the circuit shown. So first, we're going to determine how many circuits we have, how many resistors we have in this circuit. So we have 6 ohms, 8 ohms, 5 ohms, and 20 ohms. So all in all, we have 4 resistors. So we are going to find each of these resistors' power. So this is our circuit redrawn, and it is important to name the nodes, each of the nodes for this problem, since it might it might be useful in the future. We might use KCL, KVL, whichever is your strategy. You just need to make your life simpler, so might as well name each of the nodes. So you don't have to follow this, but me, I named this node A, B, C, D, and E. So those are the nodes. And so here is our overall circuit, and this problem you're going to be using KCL, or Kirchhoff's current law. So we are going to be using Kirchhoff's current law at node A. So in our circuit, here is my node A, and I just redraw it for it to be clear. And to use Kirchhoff's current law is you need to note out all of the currents that are leaving or entering, because according to Kirchhoff's current law is that summation of current in is the same with summation of current out. And what this tells us is that what goes in this node is the equivalent of what goes out of that node. And so it will give us how much current is going through this branch. So we have 0.3 amperes here going into our node, so that's positive. And we have current I2 here also going into our node in that direction, going into our node, so plus I2. And we also have 0.2 amperes also going into our node A, So you add those all up and you get the value of I2, which is negative 0.5 amperes. So using equation 1, we can get the power drawn by this resistor. So negative 0.5 squared times 6 is equivalent to 1.5 watts. Next problem is we're going to be solving the current at node B. So again, we use KCL. We know that from the previous slide, we know that I2 is moving in this direction, and we already have the value of I2. I2 is negative 0.05. Negative 0.05 amperes going in that direction. So negative 0.05 plus 0.5 amperes going into our node B minus I5. I5 is leaving node B, moving away from node B. So we solve that and we get the value for I5, which is 1 ampere. Now, using Ohm's law, we can evaluate that the voltage here is 8 volts using V is equals I times R, 8 volts. And with that, we now know how much voltage is going in this direction into our 8 ohm resistor. And so we can use this equation now to get the power that is being drawn by our 8 ohm resistor. So we have its current. So 1 based on our I5, 1 squared times 8 volts, and we get 8 watts. So this resistor is drawing 8 watts of power. Next, we find the power that is being drawn by this resistor right here. And we are going to do that by performing KCL on node C. So here is a zoomed in picture. So again, we map out all the currents leaving and entering node C. So we see here that I8 is entering node C. You might be tricked that we do not have the value of I8, but actually we have this right here, 0.3 amperes in that direction, which simply tells us that if it travels back here, that simply gives us 0.3 amperes. So now we already have the value of I8, negative 0.3 amperes. And we have I5, which is also entering node C, and we already have the value of I5 from our previous slide. We got 1 ampere. And then lastly, we subtract I9 since I9 is moving away from our node. So here's I9 moving away from our node I9. So we subtract. Now we get this equation. We solve it and we will get the current I9, 0.7 amperes. This means that 0.7 amperes is going into our 5 ohm resistor. And with this, we'll now have our resistor and our current, so we can use this equation now. P is equals to I squared over times R. We get 2.45 watts of power. This means this resistor is drawing 2.45 watts. Lastly, we are going to be looking for the power that is being drawn by resistor 20 ohms here. We will be using Ohm's law in this instance, since we have voltage and our resistance. So we can use Ohm's law, where V is equals to IR, and with that we can derive I is equals to V over R. So we have V, 15 over 20 resistance, which gives us 3 over 4. Now we have our current, and we can now use this equation. I squared times R. 3 over 4 squared times 20 will give us 45 over 4 watts of power, meaning this resistor is drawing 45 over 4 watts of power. So here is a bigger picture of the solution. Next is we're going to be solving this problem. For the circuit below, find Ix and Iy and the power dissipated by the 3 ohm resistor. So we are going to be looking for the currents passing through here and here, as well as the power of the 3 ohm resistor. So here is a redraw of the same problem, and my take here is you should simplify the circuit and combine the current sources. So we can combine the current sources by subtracting 5 from the 12. We do this because they have this opposite direction, meaning they have opposite polarities. So you subtract 5 by 12 and you get 7 amperes. So you have 7 amperes going through this whole circuit. So here is a redraw. So 7 amperes. And we can further simplify this by combining the circuits which are in parallel with each other. So here you can see 6 is parallel with 13 ohms, and so you can combine those two by using this equation. So 1 over 6 plus 1 over 13 equals 19 over 78. You take the reciprocal of this, and that is your resistance. So here it is, 78 over 19, as well as these parallel circuits. So you do 1 over 20 plus 1 over 4, you get 3 over 10. You take the reciprocal of this and you get 10 over 3. So here it is. And we can simplify that further by this right here. So as you can see, these circuits are now in series with one another, so you can combine them simply by adding them. So 3 ohms is in series with 78 over 19, so you will get 135 over 19 ohms of resistance, and 10 over 3 is in series with 7 ohms, so you will get 31 over 3 resistance ohms. So with this, we can find the current of IY by doing current divider. So use current divider to find the current at IY. So we now know that we have 7 amperes running through our entirety circuit. So we simply use current divider. So we take the resistance value opposite to the current that we want to get. So 135, we make that our numerator if you want to look for the current here. So vice versa, if you want to look for the current here, you want to use this resistance as your numerator, but in this case we want to look for the current here, so we use this as our numerator. So 135 over 19 all over 135 over 19 plus the resistor parallel to our to this one, so 31 over 3 times 7. 7 is our total current, so right there. So we will get 405 over 142 amperes. So meaning that is the current that is running through IY. Now since we already got IY here, we need to find the current here. Now we can just this is simple because we can just subtract 7 minus the current that we got here in IY, because what we got here is only a portion, meaning where did the other currents go? Well, they simply went here, and so we just subtract. So 7 minus 405 over 142 gives us 589 over 142 amperes. So this, let me illustrate it. So this is the current that is going here, and this is the current that is going through here. Simple as that. And so we have solved IY. Now we need to look for IX. Now we already know the current that is going through here. We just solve that. We just backtrack. So we already know how much current is going through here, so that's the same current that is going through here. Same current, same current. Okay. With our remaining current, use the current divider to find IX. So we know that this is the current that is going through here. 589 over 142. So that is our current going through here. And then we just use current divider again, because this current split up into two, here and here, since it's parallel, right? So current does not stay the same when it's in parallel. So in solving for the IX, again we use the resistor opposite to our resistance that we want to get. So we get 13 ohms over 13 plus 6 times our current that is going through this circuit, which is 589 over 142. And then we get 403 over 142. So that is the current here. Now, to answer the question, what power is being dissipated by our 3 ohm resistor, we go back to our previous illustrations. And so here, we are informed that the current that is flowing through our 135 over 19 ohm resistor is 589 over 142 amperes, meaning that is going through here. And so, meaning the same current is going through here. It's still 589 over 142 amperes. And with that, we can just simply use this equation. Power at 3 ohm resistor is equivalent to 589 over 142 squared times 3. So P is equals to I squared R. That will give us 51.61 watts. So here is the overall solution paper. That is all. Thank you.